And now our pre-class video for chapter 15, which deals with fluids. So first, just a quick definition of a fluid. So there's three major states of matter that we talk about. Solids, we've been dealing with a lot. They hold volume, they hold their shape. Gas, adapt volume and adapt shape. A liquid holds volume and adapts its shape. So it can move around, but the actual volume stays the same. And so fluids are substances that flow. They can take the shape of their container. The atoms and molecules are free to move, and there are no relationship between the positions. Now, we have to change the parameters that we use to describe fluids. It's going to be different than how we describe solids. And so the two parameters we're going to be using to describe fluids the most are density and pressure. So density is the mass per volume, pressure is the force per area. So let's start with density. Density is basically how much mass is in an object. Iron is more dense than water. If you have the same shape of iron and the same shape of water, the iron is going to have more mass and the same volume of water. So basically, the density tells us about that. So iron is more dense than water. And so let's look at an example. So we talked a little bit ago about neutron stars. A neutron star typically has a mass of this huge number, 2.7 times 10 to 28 kilograms, and a radius of 1,200 meters. What is the density of a neutron star? So for this, you might have to look up the volume of a sphere. Okay, but take a second and do this and see what you come out with. Okay, so when I did this, I got this answer right here. So again, you need to the volume of a sphere. So the volume of a sphere looks like this. So the radius, you would use 1,200, and basically you would divide the mass by that volume. You get answer C. Now, another thing is we'll oftentimes use this density equation to find a mass. So this way here, so mass equals density times the volume. So they always like to do this in books where you say, okay, so a neutron star is one of the most dense things we know about in nature. How much would it weigh if you could take a dime-sized piece of a neutron star? So we can, or what would the mass be? So to do that, you say mass would equal, okay, so the density of a neutron star is this number, and then this here is approximately the volume of a dime, okay, plus or minus. And so if you take these two multiplied by each other, you see what happens is the meters cubed cancels out and you're left with kilograms. So you get a number that a dime-sized piece of a neutron star is 7.5 times 10 to the 11 kilograms. If you convert that into pounds, it's 1.6 times 10 to the 12 pounds. So a neutron star is extremely dense. And basically, density is essentially how many atoms you can pack into a volume. And so a neutron star, the atoms are basically packed about as dense as they possibly can. All right, pressure. Pressure is force divided by area. The units are the pascals, which is basically newtons per meter squared. All right, so another unit we'll use a lot is 1 atmosphere. That's basically the pressure that we feel on the surface of the earth from the atmosphere, and that's about 1 times 10 to the 5th pascals, 1 and some change, the pressure from air molecules at sea level. And so an example, if I apply 30 pascals of pressure over an area of 20 meters, how much force do I apply? Well, to do that, you would take force equals pressure times area, so 30 pascals times 20 meters squared, and that would be about 600 newtons. And here's this little picture to kind of show what air pressure is kind of like. So here we have this little mechanism that somehow these balls shoot out of this little chute and they hit a scale. Okay, they basically keep hitting the scale every couple of couple of microseconds or something. And so basically, if you keep these number of these things hitting the scale will read some non-zero value. Okay, that's what air pressure is like. Air is constantly hitting our body, and so our body feels this constant pressure, okay, from air molecules bouncing off. And to find what the actual force would be, you could use some sort of change in the momentum over change in time, the impulse. So atmospheric pressure is basically the weight of the atmosphere. Air molecules are constantly colliding with you right now. This atmosphere is 1 times 10 to the 5th newtons per meter squared, or 4.7 pounds per square inch. Okay, so basically every square inch of your body feels about 15 pounds of pressure from the atmosphere. So it's pretty significant. Our bodies deal with it, but if you take that pressure away, it can be actually pretty dangerous. Okay, so now we're going to look and see how this deals with pressure versus depth of some sort of a liquid. So here what we've done is we've looked at, so here's some liquid in a little jar or something, and we're looking at it from the side. And so this little box A, that little box A is basically just, imagine if we take a box of the fluid and try to look at the forces acting on that box of fluid. If we do that, okay, there's F1, which is the force of all the water above it. There's F2, the force up of all the water below it, pressing up. And then there's mg. That water has a weight, and so it has some sort of mg force. Okay, so it's this imaginary fluid, and these forces have to balance out. Okay, so again, the weight, and then F2, the force of the water below it, and F1, the force of the water above it. And so our equation for here would be that F2 minus F1 has to equal mg. Okay, by looking at those forces. So let's use that now, and let's go through and think about it. So first of all, we can think of pressure or force as being pressure times area. So I'm going to replace the F1 and the F2 with a P2A and a P1A. That's because we want to get this in terms of pressure so we can learn about this more in terms of liquids. Now the other thing is I'm going to use that equation we used for the dime of a neutron star. Mass is always pressure, or is always density times volume. One thing we should probably stop and mention here is that pressure and density are very confusing because the letters look very similar. So I'll try to always use a capital P for pressure and then this rho for the density. You gotta be careful though, they look very, very similar. Okay, so I'm just using rho is equal to mass volume, and I plug that in for the mass. Okay, so rho is equal to mass rho is equal to density times volume. And then finally, for the volume, I said the volume is the area times the height. So of this little, we're talking about this little sort of box shape of water. So for a box shape of water, the volume will be the area times its height. And so what happens is there's an area in all these little pieces here. So the area cancels out, and this, so here, if this is our box over here, so if I draw the sort of bigger picture of the box, okay, this is the cross-sectional area. Okay, this is a horrible box, I'm sorry, but the area would be sort of this region over here. Okay, this is the area that we're talking about, the cross-sectional area for our box. But that cancels out, and so we're left with this equation here. So this equation tells us the pressure of the water, okay, at the 2 points, the top and the bottom, the top being 1 and then the bottom being 2. So we can find the difference in pressure. It only depends on the density of the liquid, usually it's water, and the height, and then of course g. So we can use this to solve problems. So let's use this now. What is the pressure 20 meters under the sea? And as a hint, the atmospheric pressure is of course 1 times 10 to the 5th newtons divided by meters at the surface of the ocean. And then the other thing is the density of water is 1,000 kilograms per meters cubed. We'll always give you that number, but you can also look it up in the back of the book. Okay, when I did this, I got this answer here, about 3 times 10 to the 5th pascals. So we use our equation that we just got, our newfangled equation here. All right, so density of water is 1,000, and then P1 is 1 times 10 to the 5th Pascal. So in this equation, the way that it works, P1 is always higher than P2. So we're talking about, you know, the top of the sea, and so it's P1 will be up here, and then P2 would be the lower one, wherever that might be. And so you plug that in, and you get, so 1,000 times 20, you're trying to find this 20 meters below, and you add those up, and we get 2.96 times 10 to the 5th Pascal. Now what you can always do is take your number for pascals and divide by the number in an atmosphere, and so actually 20 meters below the ocean, the pressure you feel from the water is about 3 times the atmospheric pressure, so it's pretty significantly different. All right, now this leads us to this idea of Pascal's principle. Okay, and so we have this equation that says the change in the pressure equals rho g times delta h. Okay, now Pascal's principle addresses how a change in pressure is transmitted through a fluid, and it's used, the biggest application of this is used in hydraulic lifts. So here's a picture of some hydraulic lifts. And so Pascal's principle is this: any change in the pressure applied to an enclosed fluid is transmitted to every portion of the fluid and to the walls of the vessel. So that means if I change the pressure anywhere on a liquid, okay, I'm changing the pressure everywhere else on the liquid as well. Okay? And it's mostly applied to incompressible fluids. That's where it's most important. And like I said, basically the only application we'll ever talk about is how this applies to hydraulic lifts, because that's the most important application. And so here's a picture of a hydraulic lift. And basically the idea is you have two pistons, a really tiny piston and then a really big piston somewhere else. Okay, and the really big piston, okay, maybe it's connected to your car or something. Okay, and the idea is you can apply a small force F1 and get out of it a huge force F2 that would lift something like your car. Okay, and so basically what we're saying here is the pressure on these two pistons has to be equal. So pressure is force divided by area. So F1 divided by area 1, which is the pressure at piston 1, has to equal the pressure at piston 2. And if you look at this, if I solve for the force 2, okay, so in this case area 2 is much bigger than area 1, and so the force at 2 is much bigger than the force at 1. Okay, and so this is the idea of how you can actually get something to lift your car up. It's a really small force, F1, but it transmits to a really big force. And again, the idea here is a change in pressure anywhere in the liquid is basically transmitted. And the trick here, okay, you might wonder, boy, this seems like we're making energy up. Well, what happens is you have to press F1 much further. So your distance D1 over here will be much further than your distance D2. So you've really got to press F1 a long distance to raise your car up a small difference. And so the work, which is work is always force times a distance, the work, which is also energy, is the same. So you're not creating energy. Okay, if you did this and tried to lift a mountain with it, okay, you'd have to push your F1 really, really far to get the mountain to even go a few centimeters or something. All right, and this leads us to Archimedes Principle. And so we'll do this in class. We'll do this example where if I weigh something in air and then I weigh it in a liquid, okay, we'll compare how those two weights work. And basically what's happening in the liquid is the liquid will be applying a force which we call the buoyant force, F sub B. And Archimedes Principle deals with this buoyant force. And so basically the buoyant force, and so now if we look at the same picture we were talking about before, let's assume that we put a block, some kind of a block in the water this time. Okay, so there'll be a force on the top, F1, and a force on the bottom, F2. The difference between these two forces is the buoyant force. Okay, and so basically it's the difference between the two pressures, all right, times the area. And so what we get there is we know our equation for difference of pressures is rho times G times H. And so essentially we get here that the buoyant force is the liquid's density times G times the volume of the liquid, because over here H times A, height times area, is the volume. Okay, well, we know that rho times volume is just the mass. So what happens, Archimedes' principle is actually kind of simple to explain. It says that the buoyant force, okay, is equal to the mg of the liquid that's displaced. And so what that means is, so this block over here, okay, this block has some volume. Okay, when it's put into the water, it displaces the water, and if I could weigh the water that it displaces, all right, and that weight would be how much the force is pressing up on it. Okay, so basically the buoyant force is equal to the weight of the fluid displaced, and we'll talk a lot about this in class. For an example, suppose you want to submerge a beach ball in water. What is the buoyant force pushing up on it? Well, basically the buoyant force is the weight of the water that would fill up the beach ball. Okay, and so if we do this, so this beach ball, I guess it was kind of big. It's about a radius of 50 centimeters, but assume it's a gigantic beach ball or whatever. Okay, and so if we do this, we would say basically the weight of this would be rho times the volume. Again, that's mass. Rho times volume is mass. And so it's the density of water times the volume of the beach ball times G. And if I plug in all my numbers here, I get 5,100 newtons or so, which is over 1,000 pounds. So if you've ever been in a pool or the ocean or a lake or something, you've been trying to submerge a beach ball completely underwater, it's very difficult to do. Okay, you've got to be able to push down, for this beach ball, about 1,000 pounds. This also lets us know whether something will sink or float. Okay, so basically there's the buoyant force pressing up on something, mg pressing down, and if the buoyant force is big enough, all right, to balance out the mg, then this thing will float. And what that basically comes down to is an equation like this. So the buoyant force is rho g times the volume displaced. Okay, the weight of your object is the rho g times the volume of the object. And so basically you get a relationship like this here, where if the volume displaced is less than the volume of the object, this will float. And what that means is if you have the density of the object that is less than the density of the liquid, it'll float. And so you can use this to do different kinds of problems. So one classic problem is, what fraction of an iceberg is submerged? Well, if you look at that, the density of ice is actually less than the density of water. So if you compare the density of ice and the density of water, you get that the comparison, if you divide these two, it's about 90%. So 90% of the iceberg will be submerged, all right? That's how much volume is displaced of the ice when it's in the water. All right, finally, we're going to talk about fluids in motion. And so we're going to talk about what's called mass flow. And mass flow is this idea of rho, the density times the area times the velocity. Okay, this is mass flow. If you look at the units of this, it's kilograms per second. It's how much mass passes by per second. And by conservation of mass, this has to always be equal. So if you have some sort of a liquid that's flowing, okay, the density times the area times the volume always has to be equal. And this one, the best example you can think about this is water coming out of a hose. Okay, so if water is coming out of a hose, it comes out at some area, okay, the cross-sectional area of the hose. So imagine, okay, and it's got some velocity. Well, if you put your thumb over that, you're decreasing the area of the hose, which means you increase the water. Okay, so this is sort of, you can think about it that way. And they call this the equation of continuity. Another example of this is water coming out of your faucet. As the water comes out of the faucet, okay, the velocity of it increases. And so again, so in this case, the density is almost always the same. So this equation works out to be A times the volume equals A times the volume. And so here, as the water flows down, it goes faster, so the velocity increases, and so the area decreases, and so the water gets skinnier, okay, as it flows down from your sink. Okay, finally, we'll talk about what's called Bernoulli's equation. We'll talk much more about this in class. All right, Bernoulli's equation, the way the book defines it, it looks like this here. Now, I like to talk about Bernoulli's equation at constant height. At constant height, these two pieces here will cancel out. So this is the more fundamental equation, but at constant height, you get this idea here. Another way to think about it is that this quantity must always stay the same. And so what this means is that when fluids go faster, okay, they exert less pressure on you. And this will pop up a lot of places in the real world. Knight has an example where you blow on a piece of paper. I suggest you try it. It's really interesting to try it. Okay, now one of the classic examples of Bernoulli's principle is an airplane wing. An airplane wing is shaped so that the water, or I'm sorry, the air, okay, air is also can be thought of as a liquid in some cases. The air above the wing is compressed. So here's a little picture showing that it gets compressed. And so it's like that hose. The area gets smaller, so the air has to travel faster on the top part of the wing. So since it's faster on the top part of the wing than it is on the bottom part of the wing, that means the pressure on the top is less than the pressure beneath the wing. And so since the pressure is less, the result is a force upwards on the wing that allows the wing to fly. Okay, another example here, and this actually can happen sometimes, okay, is if there's a really strong wind over above your roof, you can tear the roof off your house. And so here, assume there's a really strong wind over your house, and we're saying that your house has a roof of 15 by 15 is the size of it, and there's a 30 meter per second wind. Okay, air has a density of 1.29 kilograms per meters cube. So we look at this Bernoulli's equation, and again, we're going to do this for constant height. So we're assuming that basically we're looking at the top and bottom of your roof. Okay, so basically since there's wind on the top part of your roof, all right, then there'll be a pressure differential there. So the difference in pressure will equal 1/2 the density of air times the difference in velocities. Okay, we're assuming that basically the velocity underneath your roof is 0. Hopefully there's no wind inside your house. Okay, so the difference in pressures will be 1/2 the density of air times the velocity, and it's 581 newtons per meter squared. And so if we take that to find the force, we multiply the pressure times the area, we get 131,000 newtons. So it actually can be pretty significant. And so if you get a really big wind, okay, what's happening is if we drew a picture of your roof, okay, so there's a really big wind on the top, so really big velocity, so that means the pressure on the top is less. And so there can actually be a force that tears your roof off. Okay, thank you.